In this video, we're going to analyze insertion sort. But before we do that, let me remind you of something I said in some earlier videos. In one of my earlier videos, we counted actual steps. So I would have code snippets like this. For I equals 0, I less than n, I plus plus, and on every iteration of the loop, we might have done something like this. Sum plus equal I, and then close the loop. And this is C code. So this is a snippet from that, so I assume we've already created the variable I and the variable n, and n has a value, and sum has been initialized and all that. So in those earlier videos, when we were counting actual operations, we said, well, the way this works is I equals 0 will execute exactly once, and then immediately we come over and ask the question, is I less than n? If it's true that I is less than n, then we enter the body of the loop, we add I to the current value of sum and reassign back to sum. That's what this says. And then since we're at the bottom of the loop, we come up and increment I by 1. Then we come over, ask, is I still less than n? If it is, we update sum. We're at the bottom of the loop, increment by 1, retest, and so forth. And eventually we should get to the point where, in this case, if n is an integer, that I would be equal to n, and that would break the test. And even if n wasn't an integer, let's say it was 17.3, well, I starting at 0, we're adding 1 each time, we'll get to the point to where, in this case, I would be equal to 18, which is not less than 17.3, so the test would stop. Right? So if we look at this step, I less than n, how many times does that run? Well, once again, if we think of n as an integer, which is what we'll do for this type of problem, then this actually executes n plus 1 times. The loop itself runs n times, and then we have one additional time to make the test in order for it to fail. And then since the loop runs n times, the sum, I'm just going to write sum here instead of the whole line of code, executes n times, and I plus plus also executes n times. So if we look at the number of operations, we have an n, so that's 3n plus 2. And then this is our cost function, and it's a function of n. Now we also said that if n was small, for example, if n is 1, we have 3 times 1 is 3 plus 2 is 5. In that case, the 2 is a large percentage of the 5. It's 40% actually in this case. So it matters. But what if n was 1,000? Well, 3,000 plus 2 is still approximately 3,000. So in that case, it's trivial and we don't even worry about it. So when we're trying to find the order of growth of the function, we're looking at the part that carries the most weight, which is this right here. Now, in terms of the order of growth, in terms of how things are defined, we actually care about the n. And if we were looking for the big O value, big O, we'd say in this case, it's n. And we could have other cost functions. You might have had some problem where you had something like, 2n squared minus 5n plus 16. In this case, we know for large n, the n squared would be what would matter. And that's how we put the bounds on it. So what I'm getting at is, if we look at this, while I do think there's some place for thinking about individual instructions in order to understand what's happening, when you're trying to determine the order of growth, we focus on the part that generates the answer. The n here, the n squared here, whatever. And in this particular case, it comes from the loop. So really what we're saying is, for this particular case, there'll be exceptions, but for this particular case, we say, well, we're really looking at this. How many times do we ask the question, is I less than n? It happened to be n plus 1 times, and the big O value for that would be just n. And so therefore, as we perform our analysis of insertion sort, we're going to look at things like loops and how those relate to asking questions about comparisons of elements, comparisons, or swaps of data or something like that. We won't necessarily count each individual step like we did before, because this will give us what we want since we're trying to come up with an order of growth, not a specific cost function. Okay? So now let's look at this code here for insertion sort. So in the algorithms book by Corman and others, they have some pseudocode, which I've then turned into C code here. And this assumes we have an array called D that has n elements. So we have this loop here that will run. Runs what? N minus 1 times, because this starts at 1, not 0. And then we immediately will have this key value, and then we do some stuff, and then we have this loop here, and we're going to be looking at this comparison along the way. So let's look at an actual example of how insertion sort works, and this will make more sense. So let's say we have this data, 5, 1, 3, 7, and 4. And then what happens? Well, in C, this is actual C code. In C, indices start at 0. So when we have D sub 1, we're really talking about the second position. Not because it has a 1, but just because whatever this position is. Okay? And so we actually view it as we're going to have subarrays of values, and then we want to insert each additional element as we move to the right. And what we'll do then is each subarray will end up being sorted, and then we simply insert into a sorted subarray of the original elements. So when our subarray contains only the element 5, it has to already be sorted, right? Because it only contains one element. It can't be out of order. So now what we're going to do is we're going to save D sub 1, right? So this is going to be our key. And so now we're looking at these two array positions. And then what we're going to do is say, while k is greater than or equal to 0, we don't want to run off the end of the array, and D sub k is greater than the key. That is, the element to the left is greater than the value we're looking at. Then we're going to copy a value and then move over to the left again. So in this case, what we do is say, okay, 5 is greater than 1, so it copies the 5 to here. And then because we've gotten to the end of the array, we insert 1. So this subarray, 1, 5, is sorted. And now we want to insert the 3. So we're looking at these 3 array positions. We're going to look and say, we're not at the end of the array, so then we do this, D sub k greater than key, because see here k moved over by 1, so we're comparing the 5 to the 3. 5 is larger than 3, so we copy to here. Then we're going to look and compare 3 to 1. 1 is not greater than 3, so we stop this. And now we come down and insert the key, so we insert 3, and the 1 stays where it's at. Now we want to insert the 7, so we save that as key. We're looking at these 4 array positions. We're not at the end of the array, so we ask, is the 5 greater than 7? It's not. So the loop stops, and we don't even do either of these 2 lines of code, and we immediately store the key, which means we just store 7 where we already had 7, which is here. And then finally, we want to insert the 4. So we're looking at these array positions. 7 is greater than 4, so we copy the 7. 5 is greater than 4, so we copy the 5. 3 is not greater than 4, so the loop stops, and we insert the key, we write 4, and we leave 1 and 3 where they were at. So that's how it works. So what is our best case scenario here? Well, if the data is already sorted, then we'll look at this subarray, and we would just leave 2 where it's at. Then we look at this subarray and leave 3 where it's at. And we look at this subarray and leave 4 where it's at. So how many times do we ask the question, is k greater than or equal to 0 and D sub k is greater than key? Well, we need to insert 1, 2, 3, which is 1 less than the 4 elements. We need to insert n minus 1 elements. And therefore, we ask this question n minus 1 times in the best case. which means our big O here is n. Our upper bound on what we're doing here is big O of n. Worst case would be reverse order. 4, 3, 2, 1. So we start with 4, and we need to insert 3. So that means we have to copy the 4, and then we insert the 3. So I'm going to write it here. Or actually, let's just do it here. So we would end up at 3 and 4. And now we insert the 2. So we compare 2 to 4, copy that over, compare 2 to 3, copy that over, and insert the 2. Then we insert the 1. Compare it to 4, copy the 4 over, copy the 3 over, copy the 2 over, and insert the 1. So what just happened there? Let's think about it. The I loop still has to insert the, let's write it here. So I loop runs n minus 1 times. Okay. And then what happens when we insert, so if we're inserting the second element, we compared to one element on the left, plus we had one additional comparison to stop. What do I mean by that? Well, in this code, when we're inserting one number, we compare, realize that the number on the left is greater than the key, so we execute this. We come back up one more time, and either this fails or this fails. Therefore, we had to make that one additional comparison. And we insert the third element. We compare to two elements plus one to stop. And then the fourth element, compare to three elements plus one to stop. Okay? And so we work all the way down to the nth element. So this would be n minus 1 elements plus 1 to stop. So how many comparisons were there? So here we have 2, 3, 4, n. And so if we look at that, we're not going to multiply by the I loop here because this actually gives us the total count for comparisons. We're asking how many times did we say while something here. Well, then we have 2 plus 3 plus 4 plus plus n, which is equal to n squared plus n divided by 2 minus 1. Where does this come from? Well, if we want to sum the first n integers, 1 plus 2 plus 3 plus 4 plus plus n, that's equal to n squared plus n divided by 2. There's a formula for that. And actually what it is the formula would be n times n plus 1 divided by 2, which is n squared plus n divided by 2. But we didn't start at 1, we start at 2. So subtract 1 from this side, and subtract 1 from this side, and we get 2 plus 3 plus 4 down to n equals this. So what is that? So that tells us in worst case, the big O value, because this right here will be equal to n squared. Okay? So best case was n, worst case was n squared. Now we will ask, what about the average case? So in this, what we're going to do is we're going to ask how many times are we moving values over? So what we're going to do is count inversions. And what an inversion is a pair of values in the wrong order. So what I mean by that is if we had 3, 8, 5, and we want to sort this, the 3 and the 8 are in the correct position relative to each other. The 3 and the 5 are in the correct position relative to the other, but the 8 and the 5 are out of order if we want to go from smallest to largest. So that right there would be one inversion. And if we had 3, 2, 1, the 3 and 2 are out of order, 3 and the 1 are out of order, and the 2 and the 1 are out of order. So there's 3 inversions here. That is, there's 3 pairs of values that somehow we have to fix by swapping them. So what we're going to do is count inversions. And so what we want is that the average cost, or the average number of inversions, because we're looking at average case, would be the total number of inversions for all permutations, we'll abbreviate perm, of n values divided by total permutations. For example, if we have 3 numbers, how many different ways are there to arrange 3 numbers if they're distinct? That's what we're going to assume. If they're distinct, how many different ways are there to arrange them? We want to count the number of inversions across all the permutations, divide by the total number of permutations, and that will give us the average number of inversions, which leads to a cost. So let's look at some examples to get a better handle on this. So we're going to look at, say, the worst case. And let's say we have 4, 3, 2, 1. If you saw my bubble sort video, you're about to see the same example. So I need to find all pairs of values here, and the easiest way to do that is start on the left and count or pair up with everything to the right of that. So we have 4 and 3, 4 and 2, 4 and 1, 3 and 2. Why don't I count 3 and 4? Well, 4 and 3 already covers that. 3 and 1 here, and finally 2 and 1. That is not an inversion, or that is an inversion, excuse me. That is an inversion, that's an inversion, that is an inversion, inversion, inversion. So there's 6 inversions here. What if we were to reverse the order? So now we have 1, 2, 3, 4. So we went from worst case to best case. The pairs are 1 and 2, 1 and 3, 1 and 4, 2 and 3, 2 and 4, and 3 and 4. Non-inversion, 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 non-inversion. So here we have 0 inversions. So the two together, one sequence of values and the reverse of that sequence, in this case, is 6 plus 0 equals 6 total inversions for the pair. Let's look at another one. Let's say we have 3, 4, 1, 2. That's our sequence. So the pairs would be 3 and 4, 3 and 1, 3 and 2, 4 and 1, 4 and 2, and 1 and 2. So 3 and 4 is not inversion. That's the correct order. But 3, 1 is an inversion, 3, 2 is an inversion, 4, 1 is an inversion, 4, 2 is an inversion, and 1, 2 is not an inversion. Okay? So out of order, out of order, out of order, out of order. That's 4 inversions. And then if we reverse that, we get 2, 1, 4, 3. The pairs are 2 and 1, 2 and 4, 2 and 3, 1 and 4, 1 and 3, and 4 and 3. 2 and 1 is an inversion, but 2, 4, and 2, 3 are not inversions. 1, 4, and 1, 3 are not inversions, and 4, 3 is. So here's 2 inversions. And what we have here is that 4 plus 2 equals 6 total inversions. Sorry, total for the pair. Okay? So why am I looking at these in pairs, right? Because There's lots of different permutations. Why am I looking at these? Well, let's think about the logic here. I have some sequence of values. So x's here are just general values. And then so we have value A, value B, and then we look at the reverse of this. Reverse. So x, b, x, a, x, x, x. Over here we have the ordering of A and B, this. And over here, that means, of course, B comes before A. And we'll assume they're not identical. A is equal to B, or not equal to B, excuse me. Because if A is equal to B, like we have 4 and 4, reversing them doesn't change anything. Neither is an inversion. But if we look at this, if A and B, let's say they happen to be 3 and 1, then this would be an inversion. But that means over here, then we would have 1 and 3. This is not an inversion. And likewise, if we had, say, 2, 5, that would be not an inversion. Which means over here, we would have 5, 2, which is an inversion. So a sequence and its reverse together have a fixed number of inversions. Because every inversion here is not an inversion on the other side. So really what we need to do is figure out what the total number of inversions could be. And it turns out, we saw that in the worst case, it's the number of pairs of values in the sequence. So how many are there? Well, we can see here that we have n elements. We would first have n minus 1. So we had n minus 1 pairs, plus we had n minus 2 pairs, plus dot, 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 plus we'd have 2 plus 1. We can turn that around to get n minus 1 here, which will be n minus 1 times n minus 1 plus 1 over 2, and that is n squared minus n over 2. That's the number of pairs that we can have within the sequence. Okay? And we also will keep in mind that if we have n elements, there's n factorial permutations of those elements. What that means is arrangements. 1, 2, 3, 3, 2, 1, dot, dot, dot. Okay? So we're going to use that here in a minute. So let's look at an example to pull those pieces together to figure out how to calculate the average. So it doesn't matter what numbers we use, but I'm going to pick 3 numbers. Let's use 4, 5, and 6, just to keep things straight. So what are the permutations? So permutations, and then we'll count the inversions for the permutation. So one of those permutations is 4, 5, 6 in that order, but the reverse of that will be 6, 5, 4. So there's 2 permutations. Another permutation will be 4, 6, 5. And the reverse of that would be 5, 6, 4. And then another permutation would be 5, 4, 6. And the reverse of that is 6, 4, 5. So are these all the possibilities? Yes. So if we have these right here, we have 3 factorial equals 6 permutations. And these are the 6 permutations. So now we want to count the number of inversions. 4 and 5 are in the correct order, 4 and 6 are the correct order, and 4 and 5, 4, 6, and 5, 6 are all in the correct order, so there's 0 inversions. 6 and 5 are in the wrong order, 6 and 4 in the wrong order, 5 and 4 in the wrong order. So here we have 3 inversions. And so together, that's 3. 4 and 6 are the correct order, 4 and 5 are the correct order, but 6 and 5 are in the wrong order, so we have 1 inversion. 5 and 6 are the correct order, 5 and 4 are in the wrong order, 6 and 4 are in the wrong order, so there's 2 inversions. That's also 3. This is supposed to be a curly bracket. And then finally, 5 and 4 are in the wrong order, 5 and 6 are in the correct order, 4 and 6 are in the correct order, so that's 1 inversion. And then 6 and 4 is wrong, 6 and 5 is wrong, but 4 and 5 is okay, so that's 2 for a total of 3 inversions. And so the 2 together had 3, 3 and 3, and this matches our formula, which was 3 squared minus 3 over 2, right? Because it was n squared minus n. This would be 9 minus 3 is 6. 6 divided by 2 is 3. So now how do we get average inversions? So what do we have here? We need to count these up. Somehow we need to get the 9. We need to say in the numerator we have 9 total inversions, 3 plus 3 plus 3. And there's 6 permutations. So we need to get 9 over 6 is equal to 1.5 inversions on average, right, across the 6. So how do we get that? Well, we need to somehow come up with the formula for 9. So what do we have here? Well, we have there's 6 permutations, but if we look at these in pairs, where each of these is the reverse of the other sequence, there will be n factorial permutations, but divided by 2 number of pairs here. And each pair ultimately shares a total of n factorial minus n over 2 inversions. 0 and 3, 1 and 2, 1 and 2. Each of these works out to be 3. And then we said divide this by the total number of permutations, which is n factorial. So we can rewrite this then as n factorial, and I'm going to take the 2 and multiply it here to give me n squared minus n over 4. The denominator is still n factorial, and so I can cancel out the n factorials, give me n squared minus n over 4 inversions on average. Does that work here? Well, we would have had 3 squared, we have 3 squared minus 3 divided by 4. So here I would have 9 minus 3 is 6 divided by 4, which is my 1.5, just like we predicted. Okay, so what's the order of growth for that? Well, this will become 1/4 n squared minus 1/4 n. So for average case, we have big O of n squared. Okay. So we said best case was n, worst case was n squared, average case is also n squared, although the actual number of operations on average would be less than the number of operations for worst case in terms of counting, swapping values around. So what are some additional comments we can make about insertion sort? So one of those is it sorts in place. What that means is if we have these values here, other than some temporary storage, we basically just take values and reuse the same space as we're sorting, moving things around, right? We had the key that actually went over here, but then we just copied to existing locations. Some sorting algorithms work differently. They might have this is your original data, and then what you have to do is you have to create some other subarrays, and you're copying things all over the place. So if you care about not using this extra memory, you may care more about something like insertion sort. Assuming n is small, you still, because of this, you still wouldn't choose it if you have a large n. Another thing about insertion sort is that it's stable. What that means is we maintain relative order when there are ties. Let's say you wanted to sort these names. So you have Smith, Ralph, I'm just going to put R. You have Douglas, Charles, and Smith, Alex, which I'll just write A. One way you could sort these, if you wanted it sorted by last name, but then subsorted by first name, one of the ways you could do it would be to sort by first name first, which would give us Douglas, or excuse me, we would have Smith, Alex, then Douglas, Charles, then Smith, Ralph. And now that you've sorted by first name, what you do is now sort this by last name, and because you already had that Smith Alex was before Smith Ralph, since they're tied on last name, it would not change the order. An unstable algorithm might mess up the order here. Depends on how it works and what data you have and so forth. But this is guaranteed to not undo that if there's a tie here. Okay? We may prefer insertion sort to something with a big O of n log n, which is in general faster. For large n, this is much better than n squared. May prefer insertion sort to this type of algorithm if A, data is nearly sorted, or B, adding values to data that is already sorted. If the data is already sorted, then we know we just add things to the end. And you don't have to write special code to figure that out. Insertion sort just does that, which is why it could have, big O of n operations for that. Whereas some other sorting algorithms may sort of undo things in the attempt to put it back in order. So in some cases, it may actually be faster. Okay, if you have these situations. And I would even add, sometimes if you have n is small, you may do this. So there are some hybrid algorithms that may use an algorithm that has this kind of order of growth at the large scale, and then once they get the data into little subsets where n is small in these and maybe close to already being sorted, they may actually switch to insertion sort. Those type of things exist. But nonetheless, that's the analysis of insertion sort for best case, worst case, and average case.